and I would like to share with you something. All right. So in the Google Classroom, if you refer to our Google Classroom, all right. So this is our Google Classroom. Can you see my screen?
Yes, sir.
All right. In this case, I will already insert one new item which is called textbook guideline. Since some of you use the different version of the textbook, so I think it's better for me to highlight which page I'm referring to when I conduct the class. So based on this, if you open the guideline, there are two types of textbook normally used in this class. Either you use the 3rd edition or the 4th edition. Both are okay. So in this case, what has been covered has been highlighted in this table. So for example, topic chapter 1, introduction to process control, where I start with the blending process. So if you refer to the 3rd edition, it is in the page number 3. For the 4th edition, however, it is in the page number 4. So it's just a little bit different in terms of the pages. The same goes with the chapter 2. For example, the Laplace transform can be found in the appendix A for 3rd edition textbook. In the 4th edition, the latest edition, the Laplace transform has been included as part of the chapter 2. So this is the thing that I share with you for your own convenience. So in this case, you will not get confused when I'm conducting the class. So the topic that I will cover is based on these pages. So hopefully this one will help you in order to refer. The first thing is based on my lecture. I don't provide any lecture note. I don't provide any kind of the slide. So how to refer it based on this textbook. When I start my class based on the, for example, based on the transfer function, that means the added material, the textbook, the original material coming from the textbook, which referring to this page number. So I hope this one will be guide you on the topic from the textbook. So today's topic is based on the order. Still, we cover the first order transfer function. And in this case, before this, if we try to recall, it is based on the blending system, for example, where the blending system or the storage system, water storage system, normally does not cover the reaction. So today's topic is based on the reaction, where we will investigate on how mathematical model for reactive process. How mathematical model for reactive process can be derived. So this is the thing that we want to cover. So once we obtain the mathematical model, how this equation then can be transformed into Laplace until we get the first order transfer function. Alright, so in order to demonstrate how the mathematical model can be derived, so we consider the isothermal CSTR process as shown in this figure. So in this figure 1, you can see the CSTR tank, continuous stir tank reactor, where the process involves the inlet and the outlet. So here is your inlet, and this one will be your outlet. where in this case they use the F naught as your flow rate, and you have the CA naught or CA0 as indicator for your concentration. And then lastly, in the outlet, they locate the F1. And inside the tank, they have the volume and the concentration of A. C stand for the concentration, or sometimes we call it composition. So for this case, the reaction occurring in the reactor is A converted into B. So since we deal with the reactive process, so we have the A will be converted into B. And then the reaction, the rate of reaction representing A converted into B is expressed as shown below, where the RA is the rate of reaction. So this one is the rate of reaction. RA is the rate and equal to KCA. K is the kinetic rate and the CA is the composition of the component A. So for this part, concentration of component A in the feed is CA0. So here the concentration of component A in the feed is CA0. And there is no component B in the feed. So this one is the statement. No component B in the feed. Only component A available in the feed stream, which is the inlet stream. The unit of concentration used in this case study is mole over meter cube. So they specifically give the unit for the concentration, which is mole over meter cube. So here you need to note that concentration and composition sometimes represent two different things. Concentration normally is based on the molar flow rate or mole flow rate, mole concentration. However, for the composition, normally it's based on the mass fraction, for example. And sometimes in some cases, it's based on the mole fraction. However, the composition either can be mole or mass. Only here, the composition is based on the fraction. The concentration, however, is different thing because if we deal with the liquid, we represent it based on the molarity. So that means it based on the volume. So this is the difference between the concentration and the composition. The composition is based on the total mass. The concentration normally based on the volume. So that's why in this case, we found out that the unit of concentration used for CSTR is mole over meter cube. And then the assumption for this process are given below. So the tank is well mixed. So here the tank is well mixed represent the presence of stirrer. So you have a stirrer inside the CSTR, and then this CSTR, this stirrer will ensure you have the perfect mixed solution. So that means the composition inside will become uniform. So means that in this case, if we have the composition CA, so the value of composition throughout the solution will become uniform. And then the next assumption relating to the negligible heat transfer. So based on the negligible heat transfer, that means you don't have any additional heat coming into the system. No coil. So when there is no coil, you don't have any heat transfer. And this is also only a tank without insulation, without the use of the liquid transfer. So that means most probably the temperature will not going to change. When you have negligible heat transfer in this case, then normally the temperature will not be influenced. So you don't have the heat of vaporization and so on. And then number 3 is based on the constant flow rate. So you have the constant flow rate. So since we have the F0 and F1, so F0 and F1 as our flow rate, which represent the flow rate. Then we can say that when you have the constant flow rate, that means either one will be constant. So since this case, you have only F0 and F1, then maybe both will become constant. And this in conjunction with the constant volume. So here, when you have the constant value, automatically you will have a constant flow rate. So in this case, we will see later on how the assumption affecting your volume. And since in this case, we have the reaction. So here we don't consider the heat release based on the reaction process. So that means there will be no heat reaction. So delta HR will be equal to 0. And lastly, the system is initially at steady state. So this is the assumption, means that you have the initial value. So you have the starting point of the initial condition. All right. So this represent the assumption used for this process. And lastly, also we have one additional term, isothermal CSTR. So this influence the overall process. What is the variable that is essential for this process? So here, since you have the isothermal condition, then we can say that the energy balance is not needed. We assume, based on the given assumption, the temperature is not going to change. So since there is no heat of reaction, no heat transfer, and so on, then the temperature remain fixed and does not influence the reaction process given in this question. So this impact this gives the indication when we have the isothermal CSTR, then you don't need, no need to derive energy balance. So this is the indicator, since the temperature is fixed, is assumed steadily, or it assumed constant based on the isothermal condition. So let's take a look on the question. In this question, develop the differential equation. Differential equation that describe the dynamic response of concentration of component A, C8, and component B, CBT. So what is mean by differential equation? That's mean in this case, since the differential equation is based on the d over dt. So the question wants you to have dCA dt and dCB over dt. So this is the derivation or differential equation required or asked by the given question. Other than that, it's not significant since the temperature is fixed. is assumed isothermally, so you don't have any dynamic response of temperature. And for the constant volume and the constant flow rate, you don't have any volume change. So if we take a look on the theoretical model based on the conservation law, let's start with the conservation of total mass, just to see why this one become fixed. We start with the rate of mass accumulation. So here you have the overall mass balance. So in this overall mass balance, we start with the dm over dt. The mass change against time equal to, in this case, we don't know. Either the F here, the flow rate here represent the volumetric or the mass. But since the unit of concentration is meter cube, then it's better for us to use the flow rate as volumetric, meter cube per hour, for example, just for convenient, for our own convenience. If we use kilogram, then we need to multiply with the density. So since the unit of concentration based on the mole over meter cube, it's easy for us to use or to assume the F given in the form of the volumetric. So when you have the rho naught F naught minus rho 1 F1. So here the F0 and F1. All right. So in this case, we have this one, where the rho 0 here represent the rho inlet minus the rho rate of mass out, rho 1 F1. So since the M equal to density multiplied by volume, we can further include the equation d rho V over dt. Or this one, we can further expand, rho dv dt plus V d rho over dt equal to rho naught F naught minus rho 1 F1. It's like that. So based on the left hand side, you have two terms. The volume change against time and the density change against time. So we know that the density change against time will become 0. The density is not going to change against time. And for this case, it is clearly mentioned the constant volume. The constant volume. So meaning that the volume for this case is not going to change against time. So this contribute to the dV/dt become 0. So you have the equation now. Zero equal to minus rho 1 F1. Where we try to restructure it, rho 0 F0 equal to rho 1 F1. Where in this case, we can say that the density of inlet is equal to density of the outlet, which is equivalent to the constant. So when the rho equal to rho 1, then you have the F0 equal to F1. So that means this one represent the constant flow rate. Where the inlet is equal to the outlet flow rate. So this contribute or this support the assumption given here, where when you have the constant volume, you have the constant flow rate. Number 3 and number 5. So here that's why in this case, it's important to understand the given assumption, why it is given to you. Because in the end, it will definitely simplify your work. So for this part, we can see that the overall mass balance is not influenced in this process because you have the constant volume, and this contribute to the constant flow rate. Any question so far?
Saya nak tanya.
Ya, boleh?
Yang DVDT tu dia kosong sebab dia dah cakap constant volume kan?
Yep.
Yang di row DT tu kenapa yang kosong?
Okay, density is not going to change against time as well. Why? Just like previous example, today density, which we try to imagine, density of water of today is 1000. Tomorrow, still 1000. It's not going to change because this is the properties, physical properties of the component. So it's not going to change against time. Any further question? Alright, if there is no further question, then we go for the conservation of component. Now back to our question. Develop the differential equation that describe dynamic response of the concentration of component A, CAT, and component B, CBT in the reactor. So the question asks you to develop dCA over dt and dCB over dt. So for this part, we require the theoretical model based on the conservation of component. There are two components involved, so we use both components. So let's take a look on the general equation. Here, the conservation of component I. Rate of component I accumulation equal to rate of component I in minus rate of component I out plus rate of component I produce minus rate of component I consume. So since this will involve the reaction process, then we will use the production and consumption term. So let's see it. I put it again, the equation for our own convenience. So we start with the component A balance. So in this case, rate of component I accumulation. The given information in this case, the concentration of component A is based on the mole of meter cube. So that means the accumulation occur in the tank is based on the mole. So if we refer to the A, then it's a mole A. It's like that. So if the information given in the composition, then you will use the mass fraction, mass of the A. Here, however, is based on the mole of A. So you need to be very flexible on what unit given to you. So since this one, we refer to the mole A. Then we assume the mole A represented by Na. N is the mole. So here the rate, of course, you have the d over dt. that is not going to change. This is represent the differential equation, d over dt. Only here we put NA. The rate of component A accumulation against time. So the dNA over dt. So where the Na represent mole of A. So in this case, is equal to rate of component I in. So there will be component A coming into the system. So in this case, we put N dot A 0. Because the symbol used when you put 0 based on this is entering the system. NA 0. And then of course you have the rate of component I out. So dot minus N dot A 1. The rate of component A coming out from the system. Since we have the reaction in this case, so we have to include the rate of component produced or consumed. Since in this case, based on the given statement, A will be converted into B. So this means the amount of A theoretically will be decreased. Since A will be converted into B, so amount of the A should be decreased. Then that means we can say the amount of A, it should be under category of consumption. It will be consumed to produce B. So we will use the rate of component I consumed, where in this case we put minus the R multiplied with the V, where the R is your rate of reaction and the V will be your volume. The sign of minus for this case indicate that the amount of the A will be reduced. So this is tally with the theoretical based on our qualitative observation where the amount of the A should be decreased. So it makes sense for the sign to be negative. So this is the thing, the term related with the conservation of component A. No component A will be produced, so we don't use that one. So based on this, we can further expand our equation. Since we have the Na, and then we need to relate with the flow rate or the composition. So here we can say that the Na equal to Ca multiplied with the volume, where Na we can see that is a mole of A. Ca is the mole A over meter cube, and the V is the volume. So we can use this relationship and substitute into our differential equation. Then in this case, we substitute d Ca V over dt equal to Na0. So we know that here the F naught multiply with the Ca0. If we try to check, F naught in this case, let's say is the meter cube per hour. And Ca0 mole A over meter cube. So when you try to cancel it, you get mole A over hour, which is consistent with the unit of the left hand side by assuming the time given here is the hour. Or if it's seconds, still okay, because here we already have the time insert for the flow rate. So we have the NA0 equal to F0 multiplied with the CA0 minus F1 CA1. And then here we multiply KCAV. Where here, if we recall, the R equal to KCA, right? So we just substitute the unit inside the equation. So in this case, we don't use the unit or the sign negative inside the reaction. We just implement it directly into the equation, which is here. When you have negative, then it represents the amount of the A will be reduced or will be consumed. So we already substitute all of the term inside the equation. So we do the expansion. So this here, you will have the dCAV over dt. So we try to expand it. So we have V dCA over dt plus CA dV over dt equal to F0 CA0 minus F1 CA1 minus KCA V. So we already expand the left hand side of our equation where you have two terms, dCA over dt, the change of the component A against time, and then volume change against time. So here the dV over dt, it has been stated in our equation, the dV dt will be constant volume. So this is the assumption used for this case study. So means that when you have the constant volume, this part automatically becomes 0. So we can further simplify our equation. And our equation become V dCA over dt equal to F0 CA0 minus F1 CA1 minus KCA V. So we already eliminate the constant volume term. Now, based on this, we have the V dCA over dt equal to F0 CA0 minus F1 CA1. So based on the overall mass balance, we know that we have the constant flow rate. We have the constant flow rate where the F0 equal to F1. So this one we can consider as F because both have the similar value or similar flow rate. And then in this case, we have the CA1, we have the CA0, and then we have the CA. So there are three terms, CA1, CA0, and CA only. It's quite clear that CA0 represents the inlet. And the CA1 is based on the outlet. So here that leaves us what is CA. So in this case, if we take a look on the figure given, the location of the CA is inside. So since this one, we consider it as the well-mixed solution, we know that the CA in the end will exit the system at here. We exit through the outlet system. So that means based on the assumption of the well-mixed, then CA equal to CA1 because the CA1 located at the outlet. So the amount of the A will be exiting the outlet stream. So that means the correct symbol to be used should be CA equal to CA1. So this is based on the perfect mixing condition. So meaning that when we have the CA equal to CA1, then this one contribute to CA1 equal to CA. Thus, this equation can be further simplified. V dCA1 over dt equal to F CA naught minus CA1 minus KCA1 V. Or if you want to further rearrange it, you can have this dCA1 equal to F over V. CA naught minus CA1 minus KCA1. It's up to you. Both is acceptable. Either you want to stick with the VDCA1 or you can move the volume to the right hand side of the equation. Both are acceptable. So this is represent the component A balance. Any question?
Sir, just now we started the component balance with the mole because of the question is, question is based on the F, right?
Based on the concentration.
Yeah.
So in this case, if we take a look, there are two ways on the derivation. If the information give you in the form of the mass, you start with the mass of the A. If the information give you the information of the concentration, then you need to start with the mole of A. So there will be a difference on how to start the component balance. What you need to understand is which one should be developed is based on the given information, either the mass fraction or the concentration. So in this case, we standard. Concentration means the mole over meter cube. It's not going to change. The fraction or the mass fraction should be the kilogram over kilogram total. Any further question?
Saya
Ya,
nak tanya lagi.
boleh.
Saya yang equation untuk component A balance yang RV tadi apa ya doktor? Sebab tadi line start tak dengar.
Alright. So in this case, if we take a look, the conservation of component I is consists of the rate of component I accumulation. So the rate of component I accumulation here represent the dNA over dt. So this represents how the mole of A is changed against time. And then for the second term, rate of component I in, it represents the A coming into the system. How many A coming into the system? How this A is transferred into the system? By flow rate, inlet flow rate. The same goes with the rate of component I out, where in this case, it represents the rate of NA1. And lastly, in this case, it's different. If you don't have any reaction, no production, then you don't use the component I produce and component I consume. So in this case, the component produced means what is the component, what is the new component that has been produced from the reaction. So for this part, we refer to the component A, where A will be converted into B. A will be converted into B. So this means the amount of the A should be decreased. Where it has been decreased because it will consume. So this means the amount of A will be consumed for generating B. Then we need to add a rate of consumption. What is the rate of A? Being consumed by the reaction. So in order to quantify how many A has been consumed, we use the rate of reaction. So R here is the rate of reaction, where the R equal to KCA. Since the KCA in this case is based on the mole over meter cube, so we multiply with the volume in order to have the mole over time. It's like that. Any other question? Alright. Ya.
Yang negative RA itu kan,
Aha.
that one is mole over M cube kan?
Again, apa dia?
Unit R tu mole over M cube.
The R, or the unit of the R. Unit of the R. In this case, wait, mole meter cube. Unit of the R case usually 1 over time. The unit of the R should be mole over meter cube hour or second. So this is the unit of the R. Because K is the rate. Rate must have the time. In the each unit, the CA is the mole meter cube. So when we multiply with the volume meter cube, so you can cancel, you get mole of A over hour. So that is consistent.
Okay, Doctor. Thank you.
Alright.
But Doctor, if
Yeah.
usually the rate will changing based on the KCA or KCB or KCA power of 2. So we need to balance it also in the equation.
No. Okay, you need to be very clear. In this case, for PCD, process control, we use fixed value of K. So you don't need to balance it.
So we always KCA only.
KCA only. We don't use the KCA square and so on. Or KCACB. No, we just use this simple reaction. And one more thing, sometimes we also assume the conversion will not be 100%. That means there will be some remaining of the A left from this reaction. So it's much more logic to have the not fully conversion, not full conversion for component A.
Doktor,
Yeah,
R tu boleh tak kita tulis RA?
RA.
Dekat equation.
Yeah, sure, no problem.
Okay.
Any other question? Alright. So, if there is no further question regarding the component A balance, then I continue with the component B balance. So in this case, we start with the component B balance. Still, we use the same equation like here. The component principal. So in this case, we start with the rate of component I accumulation. So in this case, if we take a look, we have the dNA over dt for component A. So that means it will be the same for the component B. We just change NA into NB. So here we have dNB over dt, where the NB stands for the mole B. T is your timer. And then in this case, the first term based on the component B coming into the system. For this part, if we take a look, based on your statement, there is no component B. So this statement, there is no component B in the feed. No component B coming into the system. So that means there is no term for the B entering into the system. So that means in this case, here will be 0. And then that one represent the rate of component I in, and then minus the rate of component I out. There will be B generated in the system. So that means this B will be leaving the CSTR eventually. So that means you have the minus and B1. B is your product. We can say is your output or product. Since A will be converted into B. So A is your raw material, B is your product. So the B will be produced. It's not consumed. So based on this, normally we put plus RV. So if your product, then we can see this one should be plus RV. If your raw material, normally it will be negative RV. Plus RV, product. This in order to make sure your your amount of the A and B is consistently balanced. We use the same rate of reaction, only different sign. So if we try to further extend it, we know that the NB equal to CB multiplied with the V. So we convert or we substitute into the equation dCBV over dt equal to CB dV dt plus V dCB over dt. So this is the outcome based on the dCBV over dt expansion. So equal to negative CB1 F1. And then in this case, the R. If we take carefully, we still use the same rate of reaction for the A. So here we put plus KCAV. The rate of reaction still we used KCA. Only here you can see only the symbol positive has been changed, has been used to indicate when your amount of the A has been consumed. So this rate will transform into the production of component B. So we just change the sign, but we still use the same term, which is the R. We don't use the RB in this case, if you take notes. So based on this, we have the dV over dt. Based on the constant volume, this one will be equal to 0. Constant volume. And then here we can further rearrange our equation. Your equation become V dCB over dt equal to negative CB1 F1 plus KCAV, where in this case we can say that the CB is equal to CB1, the CA equal to CA1, since both are inside the tank and eventually will exiting the system through the outlet flow rate. So since due to the well mix, then we can assume the CB equal to CB1 or CA equal to CA1. So this contribute to the V dCB1 over dt equal to negative CB1 F1 plus KCA1V. So this is the final form of your component B balance.
Doktor, saya nak tanya lagi.
Boleh.
Doktor, kan dekat yang atas yang dekat komponen B balance kan doktor buat tong tolak mol B tu kan, mol B1 tu kan. Okey, lepas tu dekat bawah tu doktor tulis juga mol B tu equal to CBV volumetric. Lepas tu yang masa doktor tukar yang next tu, kenapa tak buat equal to negative CB1 V1 ya? Ke tak perlu?
Which one? Negative CB1 V1? Yang
No,
mana?
so you can doktor tulis negative CB1 F1 kan?
Aha.
Okay,
Oh,
kenapa?
okay. It's like this. If you take a look, this one, the NB CBV, mole of B. So this represent only the differential term. This one. That's why I change this CBV over DT. However, for NB1, the NB1 here, if you notice, you have the dot. Ada dot atas N. There will be a dot on the top of the N. So this represent the rate. So rate, that means you need to have the flow rate. So that's why in this case you have the F, not V. For the mole of B, because you have the over dt. Over dt represent your rate.
Doktor,
Ya.
the rate of reaction kan yang dekat soalan tu kan dia bagi negatif RA. Negatif tu represent nak masuk dalam calculation ke tak?
Tak, no need, no need. Here, will okay. Because here I need to make sure you very clear. Although in this case, you can see there will be a negative RA here. So here, for me, for this subject, just neglect it. Just neglect it. What we want to use only the KCA. So just to remember, for the KCA here, if it is the raw material, your equation become negative RV. So the R here, although you have the negative RV, do not change negative R, negative KCA here. Because if you negative multiply by negative, it become positive. So it's not logic. The rate of A has been increased. So we just take the term. We don't take the sign as well. So here, the R should be converted with the KCA. It's like that. Any further question? Alright, if there is no further question, we take a break for 5 minutes and we continue around 17 PM. Okay. So let's continue with our class. Before I start again, any question from any of you regarding the derivation of component balance for the case of reactive process? All right. If there is no further question, then we go straight for the B. Now, question B asks to derive transfer function that describe dynamic response of component B, CB to the change in the component A in the fit CA0. So this is the question. So now we go for the component A and component B. So this is your component A. Then based on this, and then we have the component B. So this is my component B. All right. So in this case, the term is require you to obtain the transfer function. So what we need to do is we will do one by one, component A and component B. We start with the component A. So here we obtain the dynamic state of your equation, which is the ds, dynamic state. So here we want to obtain the deviation variable, deviation form of your equation. So this require the steady state equation, where the steady state, we just follow the same equation. F CA0 minus CA1 minus KCA1 V, where we know that the V volume is constant, so you don't need to put the bar. The CA1, of course, is going to change. The flow rate is constant, no need to put the bar. CA0, CA1, CA1. You put the bar. The K, the rate. Rate of reaction normally is constant in this case. So that means you don't need to put the bar. So this is my steady state equation, SS. Where for this part, deviation form, we have the V dCA1 prime over dt equal to F CA0 prime minus CA1 prime minus K CA1 prime V. So this is my deviation form, where CA1 prime equal to CA1 minus CA1 bar, and CA0 prime equal to CA0 minus CA0 bar. So this is the deviation variable obtained from the deviation form. So once we obtain the deviation form, then that means in the next step concerns with the Laplace transform. So this is the standard. So if you don't know what to do, you just follow the step. You obtain the transfer function, you obtain the equation, then you do the deviation form. and then you put the Laplace transform. Let's say you get the derivation wrong. Still, you carry on the step. At least you will get some mark. So this is the indicator. Sometimes we count for the effort. So however, the correct effort will be taken into consideration. So here, based on the Laplace transform, we know that V dCA prime over dt become the Vs CA1 prime S equal to F CA0 prime S minus CA1 prime S minus K V CA1 prime S. So this is the transformation of Laplace for each part of your differential equation. So here, based on the right hand side, we have the CA1 on the left hand side. You have the CA1, and then on the right hand side, you have the CA1. You have the CA1. So we can rearrange our term to be included or to be located together on the left hand side. So here we have the Vs CA1 prime S plus F CA1 prime S plus KV CA1 prime S equal to F CA not prime S. So we can see that we have three terms involving the CA1 prime S. So the CA1 will be located on the left. So here on the left, we normally consider it as our output variable. And the CA1 is the composition exiting the CSTR. So it is considered as the output. So that's why we put it together on the left hand side. So we have the CA1 prime S equal to, or in bracket, Vs plus F plus KV equal to F CA0 prime S. Alright. So this is the arrangement. Where right now, if we take a look, there will be the CA1 here. This is our output variable. And then here we have the CA0, which is our inlet variable. So we want to obtain the transfer function. So the next step is based on the transfer function. So in the transfer function, we obtain CA1 prime S over CA0 prime S equal to F Vs plus F plus KV. So this is our transfer function relating to the CA1 over CA0, outlet over inlet variable. So based on this, normally when we have the transfer function, we need to make sure it follow the first order. So if we recall the first order transfer function, first order transfer function has the following form. K over tau S plus 1. So this is your transfer function standard form, where it must contain the tau s plus 1. So here you have the s, S has the power of 1, so it represent the first order. But here you have, it must include plus 1, but you don't have the plus 1. You have the plus kV. So how to convert it? So in this case, we can reconstruct CA1 prime S over CA0 prime S equal to F over F plus kV V F plus kV S plus 1. So this is the term. When I try to convert it into the first order transfer function, where now I can say that my K, the gain, process gain, equal to F over F plus kV. And the tau equal to V F plus kV. Alright. So this means I get my first order transfer function. Any question? Akif?
Yes, Doctor.
So do you get the transfer function?
Dapat.
Okay.
Okay.
Alright. Khairul Nizam?
Yes, doctor.
Okay.
Okay, doctor.
Alright. So this is your first order transfer function for the component A. So we complete that one. And then we have the component B. So we just repeat the same step. So we have the component B. In this case, we need to do the deviation form. So here I just do the short form for simplification. So here I put V dCB1 time over dt equal to negative CB1 prime F plus KCA1 prime V. In this case, the CB prime equal to CB minus CB bar. And then, okay, here the CB1. And the CA1 prime equal to CA1 minus CA1 bar. So here, this is my deviation form. And then for the Laplace transform. Vs CB1 prime S equal to negative F CB1 prime S. plus KV CA1 prime S. So this is my Laplace transform, where in this case we have the CB1. So we try to locate it together. We rearrange it. PS CB1 prime S plus F CB1 prime S equal to KV CA1 prime S. So we have like this. Now we do the factorization of CB1 prime S. Vs plus F equal to KV CA1 prime S. Now, once we obtain this one, we try to classify it according to the transfer function. Here we have the CB1, and on the right hand side we also have the CA1. If we take a look further, the CB1 and the CA1 here represent the same location of outlet stream. So the CB1 here outlet, and D here is also the outlet. This is represents some problem, because when we want to develop the transfer function, the definition of transfer function normally GS equal to output over input. So this represents the problem regarding the component B balance, because what we have here is the CB1 and the CA1. Both represent the outlet. So meaning that it's not tally with our transfer function, where the transfer function should be output over input. So for time being, since this one is represent the component B, of course, when we represent the component B, we stick. The CB must be our outlet. So if we try to rearrange it, CB1 prime S over CA1 prime S. Just for starting, we try to develop the transfer function CB1 over CA1 equal to KV Vs plus F. So based on this, we obtain temporary transfer function. Why I call it temporary? Because here the CB1 and the CA1 is not a real transfer function, because it's output over output. So we just let it be first. And then we try to figure out our transfer function here, where you get the KV divided by Vs plus F. Still, we follow the same step, where it needs to be in accordance in the standard form of first order, where the first order must be have K over tau S plus 1. So this is the guideline. Whatever you do in the calculation, in the derivation, you need to follow this same step. So you have the KV Vs plus F. So we need to convert this plus F become the plus 1. So how to do the conversion? CB1 prime S, CA1 prime S. So here we take the F outside of the equation. So you have VFS plus 1. It's like this. So when you try to expand it, it will produce the same original equation or original term. Where in this case, we can say that the gain K is equal to KV over F. And the tau equal to V over F. So we obtain the first order transfer function. Yeah.
Why can't I just bring the transfer function for component A, then substitute into the component B, so that I can get CB1 prime over CA naught prime?
Okay. Thank you. That means you are one step ahead of me. All right. So, okay, what you say is entirely correct. So this is the thing. Now, let's put into perspective. We have the CB1 over CA1 here, where you have the KV over F in bracket VFS plus 1. Like I said before, this one is not the correct definition of transfer function, where this one is your output, and this is your output as well. So how to make it correct? To obtain the transfer function GS, output over input. So since we know that our component B right now is our output, so this means this must be used in our equation. So the CB1 should be our output, since this is the product that we are going to produce. And for the input, in this case, we know that we don't have the CB0. We only have the CA0. Because the CA0 is our input coming into the system. So this supposed to be the correct transfer function for representing production of B with the input. How to obtain this? So that means we need to find the relevant transfer function, where in this case we know that CB1 we have it in the component B, CB1 prime S over CA1 prime S. And then if we take a look on the component A, we have CA1 over CA0. So CA1 over CA0, if we try to multiply it, CA0. So if we try to multiply it, then we have the correct representation of the B component. When we multiply it, we can see that the CA1 will be cancelled. So you get CB1 over CA0. Now, your transfer function is correct because it's based on the output over input. So, what is the consequence? So, since we do the multiplication, then that means our equation will be changed. So, we have the CB1 prime S over CA0 prime S equal to CB1 over CA1 is this one. This is our equation. KV F V over F S plus 1 multiply with the CA1 over CA0 is this one. Is this one. So since we want to make sure we get the correct transfer function to represent the B component, then you need to multiply two transfer functions. CB1 prime S over CA1 prime S multiply with the CA1 prime divided by CA0 prime S. So by multiplying this, that means we need to multiply the transfer function. So that means in the end, we have two transfer function involved. So to obtain the CB1 prime S, CA0 prime S, according to this equation, we can say that the F here can be eliminated. And then the rest we cannot eliminate. So we have the KV. F plus KV. And then we have the V over F S plus 1. V over F plus KV S plus 1. Alright. So this is the overall equation or transfer function CB1 over CA0. So here is ultimately we take a look on the question again. Derive a transfer function that describes the dynamic response of component B to the change in the component A concentration in the feed. So it wants you to obtain transfer function CB over CA0. So this is the way how to obtain it. We did one by one, and in the end we get the CB1 prime S over CA0 prime S. So this ultimately, if you take a look, you have the S here, the transfer function S. Originally, this transfer function and this transfer function, if we take a look, is based on the first order. Two transfer function in the form of first order. When it multiply, you can see that you have the S in the denominator. When S multiply with the S, you get S square. Then this equation in the end become second order because you have the S square. So I open to any question. So you can see how we move from the first order into second order now. So the second order normally obtained by combining or multiplying two first order transfer function.
Doktor.
Ya.
So yang ke atas tu yang output over output tu kira tak valid lah. Tak verified. Tak valid.
Sekali lagi. Once again, can you repeat the question again?
Yang dekat atas tu kan output over output.
Aha.
So kiranya yang atas tu tak valid lah.
Yeah, it's not complete. It's, we don't say it's not valid. We still use the equation, only it is not according to the definition of transfer function. is incomplete yet. If we take a look, component A. Component A, this is our transfer function. This one is correct because here the CA1, oops. The CA1 here is your output. And the CA0 is your input. So this equation is correct. The transfer function is developed accordingly, according to the definition output over input. However, if we take a look on the component B, if we try to rearrange it, the CB1 over CA1 is based on the output over output, which is incomplete. So how to make it complete? So we need to combine with another transfer function. So in this case, we combine it with the component A transfer function. So in the end, you can get the correct transfer function according to definition output over input. That is the way. Okay, any other question?
Tak ada, doktor.
Alright. So for your test, is up to here only. How to obtain the second order. So that means this one, if we refer in the test for next week, is just cover the first order only actually. So that means how to get the second order, just a beginning. It's up to there. So you study from based on the previous class, based on the chapter 1, start of page 3 or 4 until page 68, for example, like that. Dynamic behavior of first order response. Second order response, we didn't cover in the test. How to obtain, like I show here, is covered. Only up to here. Clear?
Clear, doktor.
Alright, so next week we will continue with the second order response, and then on Wednesday we will have some extra class for completing the exercise for preparation as part of the preparation in the test. I also will give you one further exercise to be completed. It's not compulsory to submit, but it's good practice for you to do it. That one I will share it in the WhatsApp group later on. So if there is no further question, then we'll finish our class for today. I thank you again for your cooperation, for your response, for your comments. Thank you very much and have a nice day.
Thank you, Doctor.
Thank you,
Thank you,
doktor.
Doctor.
All right.